In this video, we'll take a look at a couple of different properties of power series, integrals, derivatives, and we'll wrap it up with one nice problem at the end. So here's my question. I want to find a power series to represent 1 over 1 minus x squared. Now, certainly you can go through that process. F of x, f prime of x, f double prime, triple prime, put in the center of the series, do your f of a plus f prime of a, x minus a, and so forth. But if you can link this up with something that you already know, that makes it a little bit easier. Suppose I had 1 over 1 minus x, and I asked you to derive 1 over 1 minus x. Well, I could use the quotient rule, or I could just say that this is 1 minus x to the negative first power. And so if that's f, then f prime is negative 1 times 1 minus x to the negative second power times the derivative of the inside, which is negative 1. And now these two negative 1s go away, and I end up with 1 minus x to the negative second. Hey, what do you know? That's 1 over 1 minus x squared. So my point is, if I know a series for 1 over 1 minus x, and I derive it, I'll have the series for 1 over 1 minus x squared. Right? So we know that 1 over 1 minus x is equal to 1 plus x squared plus x to the third plus x to the fourth till I get to x to the n, right? So now, derive both sides. We already figured out up on the top that if I derive 1 over 1 minus x, I get 1 over 1 minus x squared. When I derive the right-hand side, the derivative of 1 is 0. The derivative of x is 1. Derive x squared, and I get 2x, right? So I derive that, I derive that, I derive that. The derivative of x to the third is 3x squared. The derivative of x to the fourth is 4x to the third, and so forth until I get to n, x to the n minus 1. All right, so there's a couple of things that come out of this. Well, first of all, I get a nice series out of it. I guess that's a nice advantage. The one thing is you can derive a series term by term. And when you do that, the interval of convergence remains the same. And by the same, I mean same as the original one. Okay, so if the 1 over 1 minus x converge between negative 1 and 1, then 1 over 1 minus x squared also converges between negative 1 and 1. And if you want to graph the two series and show that you get the same thing, right? If you want to graph 1 over 1 minus x squared and then you want to graph the polynomial approximation, you can do that. And you should come up with graphs that sit on top of each other between negative 1 and 1 and do not sit on top of each other outside of that. All right, how about integration? Integration works too. So here's my task for integration. I want to find a series. Sometimes we might call this a series representation for the inverse tangent function. Now, yes, you can do inverse tan of x, and you can derive the inverse tan of x and do a third derivative, a fourth derivative. And, if you want degree 10, do 10 derivatives, or do enough that you see a pattern. But I also know something about integrating, and that is I know that if I integrate 1 over 1 plus x squared, I'll end up with the inverse tangent of x plus some constant. So if I can find a series representation for 1 over 1 plus x squared, then I just have to integrate both sides, and I'll end up with a formula for the inverse tangent of x. All right, so what if I tried that? What is 1 over 1 plus x squared? That's essentially 1 over 1 minus x, except that I have a negative x squared on the inside here. So the square should go on the inside. All right, so now is that the same thing? Sure enough, two negatives make a positive, and I'm done. So my first term is 1, and then my ratio is negative x squared. So if I start with, instead of having 1 plus x squared plus x to the third plus x to the fourth, right? That would be for 1 over 1 minus x. Instead, I'm going to replace all those x's with negative x squares. So I get 1 plus negative x squared plus negative x squared squared plus negative x squared to the third plus negative x squared to the fourth, and so forth. Let's clean this up a little bit on both sides. And I end up with 1 over 1 plus x squared equals 1 minus x squared. Now, this is going to end up being a positive, right? Negative squared gives me a positive, so I get plus x to the fourth minus x to the sixth plus x to the eighth, and so forth. So now I have a representation for 1 over 1 plus x squared. Really, what I should do at this point is I should replace all those x's with t's and set up a dummy variable, because I don't want to integrate from 0 to x when x is already one of my variables. So let's take a look at switching variables, just so that we don't have two variables, or the same variable that means two different things. So I'm going to set up my left side as 1 over 1 plus t squared, and on the right side I'll do 1 minus t squared plus t to the fourth minus t to the sixth plus t to the eighth, and so forth. And then I'll just integrate both sides from 0 to x with respect to t. Right? I'll integrate this side from 0 to x with respect to t. And what will happen on the left side is I'll get the inverse tan of x minus the inverse tan of 0, which is just the inverse tan of x. On the right side, I'll get all of these things evaluated with t's, and then when I go to do the second part, I'll evaluate them at x and at 0. The 0 part will go away, and it'll actually subtract off that 1 at the end. So what will happen is I'll end up with an integral of 1 being x minus x to the third over 3 plus x to the fifth over 5 minus x to the seventh over 7 plus x to the ninth over 9, and so forth. So there it is. I've got a representation for the inverse tangent of x, which I did not have to do by taking individual derivatives. By the way, if I want to represent this as a series, I could. I can see the signs are going to alternate, so I'll have a negative 1 to the n. There'll be odd powers, so I'll have an x to the 2n plus 1 on top, and a 2n plus 1 on the bottom. Whatever the power is on top, the number is on the bottom as well. And then I just want to make sure they alternate in the right way. So if I start with n equals 0, does that work? Yes, because I end up with an x to the first over 1. So let's start this at n equals 0 to infinity. So this is the series for the inverse tangent. Right? And because I was able to integrate term by term, which I can do, right? If I can derive it term by term, I can integrate it term by term also. So what can I use this for? Well, suppose I wanted to know the inverse tan of 1. And this might give us some motivation for why we would want to do such a thing. If I want to find the inverse tangent of 1, the inverse tan of 1 should then be 1 minus a third plus a fifth minus a seventh plus a ninth. Now, you already know what the inverse tan of 1 is, right? The inverse tan of 1 is pi over 4. Try it out on the other side, right? Pi over 4 has got to be less than 1, right? Pi is 3.14, so you're looking at 3/4, maybe a little bit more than 3/4. So you get 1, and then you subtract a third, now you're down to 0.67. Then you add a fifth, and you're up to 0.87. And then you subtract 1/7, and you're down a little bit more. Up and down, you're wobbling your way towards pi over 4. So that's how they evaluated inverse tangents before they had nice calculators and TI-34s and whatever that we could substitute numbers in for. All right, let's try one more sort of nice wrap-up problem that involves series. So here's my question. I draw a nice big line segment across here. Determine all values of x on the interval from pi to 2 pi, for which this series converges. And here's the series. The sum from n equals 1 to infinity of 2 to the n cosine of x to the n over n squared. So for which this thing converges. I want to try to make a nicer infinity symbol up here. There we go. All right. So the first step is I need a ratio test. I need to take the limit as n approaches infinity of 2 to the n plus 1. This thing over here, that cosine of x to the n, it might make it more comfortable if I wrote it like this, cosine of x to the n plus 1. And on the bottom, I replace that n with an n plus 1, and it gets squared. Okay, rather than divide by the original, why not multiply by the reciprocal? And I get an n squared 2 to the n cosine of x to the n. And I want to force this to be less than 1 and find out for what values of x that's true. Well, this looks a little messy, right? Let's separate them like we did before. I get 2 to the n plus 1, 2 to the n. How about the n's? I got an n squared on the top, n plus 1 squared on the bottom, and then I've got a cosine of x to the n plus 1 on the top, cosine of x to the n on the bottom. And I want that ratio to be less than 1. All right, well, it turns out it's not too bad. These first two terms just give me a 2, right? N plus 1 of them on the top, n of them on the bottom, one more on the top than on the bottom. If I apply the limit as n approaches infinity, this piece here just becomes a 1. Even if you expand it out, you'll notice you have an n squared on the top, n squared on the bottom. All right, L'Hopital it a couple times, you'll just get 1. Over here, again, I've got n plus 1 cosines on the top, n of them on the bottom, so I've got one more cosine on the top than I do on the bottom. This leads me to the absolute value of 2 times the cosine of x is less than 1. All right, divide both sides by 2 and expand it out, and I have that the cosine of x has to be between negative 1/2 and positive 1/2. Now, that means that I need to find values of x that satisfy that. So take the inverse cosine of everything, but then don't forget what the original problem said. The original problem said I want values on the interval from pi to 2 pi. And there's a reason for that, and you'll see this when we come up with the answer here. So the cosines are the x-coordinates. So I'm looking for places where I have a negative and I have a positive. Where is the cosine equal to negative 1/2? Okay, it's equal to negative 1/2 in the second quadrant and in the third quadrant, but the only place that fits in here has got to be in quadrant 3, right? This is only quadrant 3 and quadrant 4. So where is cosine negative 1/2 in quadrant 3? Happens at 4 pi over 3. All right, where is the cosine equal to positive 1/2? That happens in quadrant 1 and quadrant 4. But again, if I'm only going between pi and 2 pi, then the answer's got to be in quadrant 4, not in quadrant 1. That's 5 pi over 3. So actually, this should be just plain old x. So x is between 4 pi over 3 and 5 pi over 3. Now I need to test the endpoints. All right, so let's look and see what happens when x is equal to 4 pi over 3. All right, when x is equal to 4 pi over 3, then I end up with a series that says 2 to the n cosine of 4 pi over 3 to the n over n squared. Well, we already figured out that this thing here, cosine of 4 pi over 3, is negative 1/2. So I end up with a 2 to the n negative 1/2 to the n. Well, isn't that just negative 1 to the n? That's my numerator. What about the other side? What about x equals 5 pi over 3? Okay, if x is equal to 5 pi over 3, I end up with a series of 2 to the n cosine of 5 pi over 3 to the n, which is 2 to the n times positive 1/2 to the n That's just 1. All right, so now the rule is we have to figure out whether or not these series converge. All right, so this becomes the sum of all the negative 1 to the n over n squares. This becomes the sum of all the 1 over n squares. This guy right here is a convergent p-series. I could see that. This thing over here, you can either say it's an alternating series and converges, or you could even say, well, because it's converging when I take the absolute values, in other words, knock out that negative 1 to the n, and just leave a 1 in the numerator, now I got a 1 over n squared. Again, it's a convergent p-series. So this thing includes both the endpoints. This includes the 4 pi over 3, and it includes the 5 pi over 3, and none of them are conditional. They're both absolute convergence at the endpoints. That's why, by the way, I restricted my values to be between pi and 2 pi, because I wanted to find a spot where the two of them met on a continuous interval. If I had gone strictly by the inverse cosine definitions, I would have ended up splitting between quadrants, and I didn't want to do that. So I went between pi and 2 pi so that I would get an answer that's on a continuous interval. All right, there you go. Series tests, radius of convergence, and endpoints.